Oh, okay, I will now begin the lecture for the lithography part and then data analysis. Actually, last Thursday, you got the clear idea about the lithography, okay? And today, we will go over a little bit more the technology what currently being used in the industry also. Okay. All right. So I think there are a couple of different techniques for lithography. Okay, particularly for nanoscale now. Okay, it's not micron, nanoscale. Okay. So first one, conventional lithography. Okay. So you learned a lot in the last class, and then also you are told about the immersion lithography. Yeah, you are introduced to immersion lithography. I'll quickly go over again. And then extreme UV lithography, that is this one, extreme UV lithography is now being used in high-end the IC industry. And then now some other additional the methodology currently being researched for the next generation. Okay, so the one of them is the X-ray lithography, and then e-beam lithography, and then now nano imprinting. I will just quickly go over this type of technology. Okay, now let's look at this the lithography chart. Okay, when you look at this, you see the top. Okay, you learned the AutoCAD, right? Actually, that is this one, right? AutoCAD data of the micro, but actually the nanostructure too. Okay, once you develop the CAD design, I told you I sent this data to the company, right? Since we don't have the e-beam writer, we don't have the laser beam writer. Actually, we have an e-beam writer, but this is for research purpose, okay? But the commercial the use of the e-beam writer is to make actually the mask. Okay, using this the e-beam writer and then laser beam writer, now the mask can be made. Okay, you learned what is mask, actually metallic pattern on a glass, right? So those masks can be used for the contact, proximity, and then projection lithography. Okay, so then actually this mask can be applied to dim UV lithography, and then extreme UV lithography, also X-ray lithography, and then even projection lithography, ion beam projection lithography. But the currently industry use these two. Okay, these three are actually currently being used, the researched. Okay, so now with that the mask, actually what? You can do the actual lithography, okay, by coating the resist on the substrate, and then do the exposure, okay, do the UV exposure, and then do the developing. Then you can have some of the micro or nanostructure on substrate, okay. Actually, by doing this lithography, you can have this, but you can incorporate the wet or the dry etching process. Okay, so this is actually this diagram shows the overall idea about the lithography, and here I didn't explain the direct writing. Actually, the major industrial use is the projection lithography this side, but research-wise, we can directly write the pattern on the microstructure or the substrate also using e-beam or the laser beam writer. I will explain this later too. Okay, so I think you have seen the diagram, right? So our clean room used the contact lithography because this is the very simple lithography tool. Not many optical lenses are involved. Very simple and then cost effective. So many research universities, Harvard, MIT, or mostly used they have these the contact lithography, Penn State and others. Okay, and some of the university also or research institute have the projection that the lithography tool, but it's low end, not industry level. Okay, so we learned. Okay, so for the lithography, what should we do? First, we need to apply the photoresist on a substrate, okay? So you see the photoresist here, the pipette can take some of the small amount of the photoresist and then apply on the substrate, okay? And then substrate is the spinning, and then depending on the spin speed, we can get certain amount of the photoresist thickness, okay? So that is the photoresist. And then what? Actually, the after photoresist spin coating and then the bake, soft bake. And then we can expose the UV through a mask. Okay. So the glass has certain pattern inside. The metallic, particularly this is normally made by the chromium. Okay, so through this the transparent glass pattern, now the UV pass through, and then the generation of the chemical reaction on the photoresist. So yeah, some of the pattern you see the area can be removed or the other area remains by the reaction enhanced by the light. Okay, so we can have this type of the pattern transfer on some substrate, right? So these are all the photoresist patterns, okay, after developing. Okay, pretty nice, right? So for this the photolithography, we use lens, right? And also the mask. You heard the diffraction, right? Light diffraction all over this area, and then we collect the diffracted light and then make them into a focus, right? So the performance of the lithography, yeah, is actually the assessed by the resolution, right? If the resolution is small, that means some of the feature in between these can be resolved, right? Okay, so pattern A, pattern B can be resolved, okay, by the lithography tool. So smaller is better, right? This case, the resolution smaller is better, right? To make this the resolution, okay, this is the equation, simple equation. Okay, to make this resolution small, what you can do? There are two different ways. Okay, the process factor normally is the set. Okay, it doesn't change much. But what you can change, we can make this lambda small. Or we can make this numerical aperture big or large, right? Okay, so you learned, okay, we will see, okay, we need to approach two different the directions, okay? Make this lambda small or make this NA, numerical aperture, large, right? Okay, so how we can make the numerical aperture big? There are many different, actually two different ways, okay? What is making this the D big? Okay, D is the diameter of the lens. Okay, so make the very large the lens. Okay, they can make the NA big. Another one is this one. Okay, and is the index of the refraction. Okay, so by increasing the index of the refraction, okay, we can make this NA big. Okay, index of the refraction on the light medium means you see this light pass through this medium, right? So originally this medium was air, okay? But the immersion lithography, you learned immersion lithography, right? We change this into the water, okay? So we'll go over a little bit more later. So that way, we can make this NA big. So making this NA big, now the resolution can be smaller. So the smaller pattern can be generated and then can be used to make the smaller size of the transistor. Okay, so that is the main idea, okay? Okay, you see the D, actually the depth of focus also, okay? So depth of focus is also important, okay? So depth of focus case, that can be given as the idea. Okay, now to make this the depth of focus, you learned about this depth of focus, right? So how to make this the depth of focus large? When you learn the last class DOF, this depth of focus, it's large is better, right? In this case, how to make this large? Okay, then NA should be small, right? So actually, to make this the resolution big, NA should be big, but to make the depth of focus, NA should be small. So it's opposite direction, okay? So in industry, they have to find some of the range, okay, to get the better the depth of focus, to get also the good the resolution. So it's tricky, okay? So but they based on the experiment or the analysis, they find their own the values matching both direction, okay? Okay. So, oh yeah, I didn't show this. Okay, so small depth of focus, large depth of focus, right? Normally this large depth of focus is better to define the pattern in the various the topology of the structures, okay, to generate the fine pattern, fine image on the various height on the surface structures. Okay, so the large DOF is always the desirable. Okay, so after making this the device, okay, or using this lithography, okay, we need to see, okay, whether these the images are well defined, right? So I think you know how to use the optical microscope, but I will show you. Actually, we need to measure this width also. We need to measure also this height. We need to measure also this gap, whether they are defined as we planned, right? So for that, I want to show you one video. Yeah, how we analyze, how we measure those type of the parameters in the clean room. Okay. There are a couple of the tools we use. First is the optical microscope. Second one is the scanning electron microscope. Third one is the profilometer. Okay, you will see how they can be used to monitor this the lithography, the process, the performance. Okay. Okay, so you see this the optical microscope. Okay, so I will play the video. Okay, you will watch this video around 10 to 15 minutes. Okay.
Introduction to optical microscopy and the Light's Ergolux reflective microscope. Optical microscopy is a measurement technique which uses the reflection of visible light off of the surface or some plane of a sample and a series of optical lenses, which allows us to magnify and focus an image of the sample being investigated. It's a non-contact and non-destructive technique. These microscopes allow us to see and measure the surface structure of materials, and they also allow for the observation of deeper structures in opaque materials. Oftentimes, an interchangeable objective lens is present, and this allows the magnification of the microscope to be altered, typically from 5 times to 1,000 times magnification. The image is typically observed at the top of the tool using an eyepiece, but some can be connected to cameras and computers to allow for digital imaging, saving, and the taking of measurements. There are two basic modes of operation for optical microscopes: bright field and dark field imaging. In bright field imaging, the light source shines light onto a mirror such that the light is reflected straight down onto the sample. This light then reflects back off of the substrate and sample, passes through one or more magnifying lenses, and then produces an image in the viewing field. This image displays the entire sample surface because light is being reflected from the entire surface below. In dark field imaging, the light source shines directly onto the substrate and sample, but it is at a low angle, off the axis of illumination, with respect to the substrate. Most of this light reflects away and never passes through the lenses above. Some light, however, which is scattered by surface irregularities, makes it
Okay, looks some of the difficulty to. Okay. So I will come back. I think some of the let me try once again. I think it was logged in too long. Or just 1 minute.
right of the tool. We can turn the light source on and off with this red button, and we can adjust the voltage and therefore light intensity by rotating that knob. Start by turning on the power switch, then rotating the power adjustment knob clockwise to increase the voltage and light intensity or brightness. Normal bright field operating voltage is between 5 and 7 volts. However, for increased magnification images and/or for dark imaging, you may require higher voltages. That said, the intensity should never be turned up past 12 volts, as this can damage the light source. Finally, the light source should always be returned to the lowest intensity and then turned off when not in use. If the power is left on, the light housing may overheat.
I think I didn't share just after playing. Okay, just a minute. I realized I didn't share the screen. Okay, sorry for that.
May require higher voltages. That said, the intensity should never be turned up past 12 volts, as this can damage the light source. Finally, the light source should always be returned to the lowest intensity and then turned off when not in use. If the power is left on, the light housing may overheat and cause failure of internal fuses and thus no more light source. Before we can image a sample, we have to load it onto the stage. Samples should always be loaded onto a clean room napkin, which rests above the stage. This protects the microscope stage. Once loaded, grab the napkin and center it above the stage. After this, use the stage adjustment handle to roughly position your sample below the objective lens of the microscope. The stage adjustment handle allows us to properly orient our sample underneath the objective lenses. To avoid interference or unwanted accidents, you should always use your right hand to make these stage adjustments. This stage has both a locked and unlocked position. Down is the unlocked position and up is the locked position. When the stage is unlocked, you're free to move the stage in any X or Y direction. Just grab the black stage adjustment handle and move the stage accordingly. When the stage is in the locked position, use the two silver knobs for fine X and Y stage movement accordingly. From a top view of the tool, we can see that there are various apertures and filters. All the small gray levers should be in the up position as shown. And for bright field imaging, all the adjustable black filters should be pushed in so that they are flush with the right side of the tool, as shown here. For dark field imaging, keep the silver levers up, but pull this black sliding box out towards the right side of the tool. On the bottom right side of the tool, this two-way switch allows us to rotate through the various objective lenses. Pushing forward once rotates clockwise to the next objective lens, while pushing backward rotates counterclockwise. Whenever loading or removing a sample, be sure that you have the lowest magnifying power lens in the bottom position. This gives you more space between the lens and sample, because weaker lenses protrude much less than higher powered lenses. Also, the 50 and 100x lenses are much more expensive. So always begin at the lowest magnification, focus, and then proceed to higher magnifications. Depending upon the distance between your eyes, you may need to adjust the viewing lenses, which themselves happen to be 10x lenses. Simply grab and pull outward or grab and push inward to make the necessary adjustments. On the left side of the tool, we have the coarse and fine focus adjustment knobs. These knobs are used to move the stage and sample up and down along the Z-axis. We begin with the coarse adjustment knob for two reasons. First, it's used to move the stage to a safe position, far below the objective lenses, before loading or removing a sample. After this, it's used to make coarse focus adjustments. Notice that we always use our left hand for focusing, as this will avoid bumping the stage and otherwise interfering with proper tool operation. When imaging a sample, always begin at the lowest magnification and then adjust coarse focus. After this, use the fine focus knob to more precisely focus your image. Once this is done, rotate to higher magnifications and then adjust fine focus as needed. As you continue to increase the magnification, it will also become necessary to increase the light source intensity. Remember, use your left hand to adjust the coarse and fine focus, and use your right hand to lock and unlock the stage. Use the stage adjustment lever and knobs, and switch between objective lenses. All right, now that we've reviewed the major components, functions, and safety concerns of optical microscopes, let's get started and image a sample. Turn on the microscope power, the light source, lower the stage to a safe working distance, rotate to the lowest power objective lens, load your sample, and move the stage to the proper position below the lens. The digital components of this optical microscope require a computer and integrated software. Start by clicking on the Cube Capture Pro icon. Once the software opens up, click on Acquire, now Video Digital. This opens the Video Digital toolbar. The next thing to do is to click on Preview. Now we see a live preview of our sample. At this point, we'll want to adjust our coarse and fine focus. Do this by rotating the coarse adjustment knob forwards and backwards until the image becomes clear. Now we can adjust our exposure. By sliding this bar, we're actually increasing or decreasing the time allotted for light to strike our digital detector between consecutive snapshots. We can also increase our image brightness by increasing the voltage on our light power source. At this point, we can use our stage adjustment knobs to view a feature of interest. Once our sample is properly positioned and in focus, we can move to a higher powered objective lens. Now it's simply a matter of repetition. Adjust the stage, adjust our focus, and change the objective lens. And remember, when going to higher powered magnification lenses, it may be necessary to increase the light intensity. last thing to do would be to make some final adjustments to the exposure. Now we're ready to hit snap and take a digital still image. At this point, you could make some color and contrast changes, but they're not absolutely essential. Now we can start taking a measurement. The first thing to do is to click on this icon for active spatial calibration. In the drop-down menu, choose the option which correlates to your current objective magnification. Now click this Measure Distance icon for manual measurements. Now using the mouse, simply click and drag and release to find your measurements. These happen to be in microns, 5.12 and 6.50 microns. When you finish, click that red X to delete all your distance measurements. Close your measuring tool. Now return to the top and you can select the zoom to point tool if you'd like to do a digital zoom and take those measurements again. Click on the hand icon to move your image, then click back to the measurement tool. Again, click, drag, and release. If you'd like to save your processed image and measurements, go to the top and click File. Now click Save or Save As, and you can type in the file name and save your information. Now the next thing you may want to do is go ahead and gather dark field data. As you can see, when you switch to dark field, you have much less light and therefore your image is black. This happens because the only light that makes its way up through the lenses to the detector is light that is scattered off of surface irregularities. To get an image, we increase the exposure time until we can see something. Continue to adjust the exposure time until you have an image with adequate contrast. Then you can, of course, perform the same focusing, changing of lenses, measuring, and saving as previously shown for bright field imaging.
Okay, so regarding this, the dark field imaging. Okay, and then regarding this, the dark field image, actually to get the more information about some of the particles. Okay, so because of the lot of the scattering, light scattering, and then the reflection on the particles, we can easily capture those particles better in the dark field image. Okay, I think it was kind of a bit long to get an idea about how the microscope is used to measure and then see the features in on the surface of the wafers after the lithography. Okay, that is the microscope is the widely, actually the most commonly used in the clean room after the check the functions of the fabrication. Okay, all right, and then actually I will continue some of the stuffs. Okay, just a minute. Okay, like I said, that okay, so we can check the patterns and then the defects on the lithography, but the main idea of this the lithography is to transfer the pattern onto the substrate, and then the industry actually try to make the smaller and smaller the features. I think you learned about the Moore's law, right? Making the smaller transistor actually is giving them a more power to win the technology and market. So companies are always try to make the smaller features. So Now we only focus on now the resolution side. Okay, so now we will talk about this resolution once again. Depth of focus is a little bit different. Actually, that doesn't have the much of the room to move around, but let's try to focus on the resolution. Okay, so like I said, now the main idea of the reducing the resolution is the having the smaller the wavelengths, and then the making large NA, right? So that was the main approach that you can try. So here is the light source available. Okay, so here you see the first generation of the optical lithography used the G line. Okay, this UV light was used around 1970 around. Okay, and then I line took over around 1980. Okay, this one was 1960 through 70 around. Okay, and then the KRF was applied. This one is around 1990 around. Okay. And then now, most of the lithography now being used by the ARF. Okay. Okay. ARF is the argon fluoride excimer laser. Okay. And then now actually the many trial was made to use this just the fluoride laser, F2 laser, but there are a lot of the technical issues. The main reason of this, the difficulty of this, the F2 laser is, you know, our light pass through the glass, right? I think you learned about the band gap energy, right? So band gap energy in the previous, I think Tuesday class, okay? So the reason why the light, the visible, this UV light can pass through the glass is the band gap energy of the glass is pretty large. So the glass doesn't absorb. Glass doesn't absorb the light, the wavelength light. So this can just freely can pass through the glass. But when the wavelengths get smaller and smaller, the energy of the light increase. Actually now the 157 nanometer the wavelength energy is actually the comparable to the band gap energy of the glass. Now in this region, this fluoride laser, actually this light is observed in the glass. Regular glass, okay? So that means the lens is not going to work as the lens, okay? That is going to work as the observer. That means the light cannot penetrate through the F2. This 157 nanometer light cannot penetrate through the glass. So that means now the lithography system is not going to work, right? So that's why after this, up to this one is regular optical system. From here, it's not the optical system, like a penetrating optical system, not penetrating, okay? Not penetrating things, okay? Okay, so this is the boundary, okay? Now industry is facing now the boundary. They have to develop the new technology, but until the new technology is developed, they are now pushing this boundary as much as possible. That is actually the emergent lithography, okay? Emergent lithography case, the 153 nanometer wavelength is still can be used, okay? But now the resolution can be increased by the water, okay? By applying the water, because like I said that originally this N, yeah, this original N is in the air. in the air, it's 1. Okay, but by having the water, now this n value changes into 1.4. So that decreased the R, that much amount. Okay, so now 40% of the increase, okay, NA, okay, that decrease around the 70% of the resolution. Okay, so that is the main idea of the emergent lithography. So, but the problem is how we can handle this the water underneath of the projection optics. Actually, we can apply the liquid underneath of the optics, and then we can take out the liquid through this, right? And then many different approach was designed, okay? But eventually this system has been developed. Now the Intel, Samsung, and TSMC, all the industries are now using this the lithography technology. Okay, but this also has some of the problem because the water has some of the impurities inside, and this only the impurities are not only from the water. You know the wafer. You see this water pass through the surface of the wafer, right? The wafer already have some of the photoresist and some of the particles on there. So that actually can be the source of the defects, right? So, and also the temperature variation and then the thickness uniformity of the water layer, all this is, and also this type of the bubbles, water bubbles is going to change all the optical, the passage, and then the deflection, and then or yeah, right? So but still, you know, the having this the light still 153 nanometer light, but the pattern, okay, the lithography pattern can go down to even the 50 nanometer easily. Okay, but like I said, if there is a certain bubble on here, then actually the defect can be generated. Okay, so but what still this light can be used. 153 nanometer light can be used. So like I said, after this, we have to use some other different type of the optics. Okay, so now what the new technology has been developed is it's called the extreme UV light lithography. Okay, this is called the EUV lithography. Now the Intel and then Samsung, okay, they used this technology for the front-end devices. Have you heard about the 5 nanometer, the transistors, or the 7 nanometer transistor? When Intel, you know, when Intel they give the advertisement, they talks about 5 nanotechnologies, transistors has been developed in their company, or those type of things. Okay, so for that, you know, even though the extreme UV, this lithography can do down to 50 nanometer, some case around 40 nanometer, 30 nanometer, but that is very challenging. Okay, so to realize those the few nanometer transistors, actually the extreme UV lithography is the critical. And the light source for the extreme UV is now how much? The wavelength of the UV is the 13.5 nanometer. What is the emergent lithography light source? 103 nanometer. 193 nanometer wavelengths now go down to 13.5 nanometer light wavelength. Okay, so actually for this now the laser is used. Okay, actually for this the synchrotron radiation source can be used. Okay, but it's very difficult to have the synchrotron radiation in a plant, right? It's very expensive and it's very sophisticated tool. So the industry doesn't use. Instead, what? Now the laser plasma source, okay? Okay, laser plasma source are being used, okay? So this the CO2 laser with the thin plasma. So here is the CO2 laser, provide the CO2 laser to the what's the optical the system, and then actually the small thin drops are placed in here, and then using this the magnet, and then applying the electrical power, thin plasma generated in here. By combining this the thin plasma and the CO2 laser, we can have 13.5 nanometer light coming out through this the light source. Okay, so this is the UV lithography light source. But I told you the band gap energy, the energy of this light is quite beyond the band gap energy of the glass. So it cannot penetrate through the glass. No way. Okay, it doesn't go. Okay, only this, and then what? It's absorbed inside of the glass. So for this the lithography, what is used instead of the parent the glass, it used the reflective mask. Okay, so having this the reflective mask, okay, now this is the light source goes in, and then with a certain pattern of the observer, and then the selective the reflectance comes here, and then another the reduction optics, okay, and then go back, and then go into, now we can to have some of the light reflected from this, and then some of the pattern can be transferred onto the substrate. Okay, for this what kind of the lens can be used? This is the multi-layer coating of the molybdenum and then silicon. Okay, having this the multi-layer of the coating, we can have the reflection, light reflection. Okay, so you know about the constructive and then the destructive the reflection. Okay, so having those type of things, okay, the reflection can be made. Okay, but for the pattern of the design, we this type of the observers can be placed on top of this the reflector. So this observer the remove the light on this the surface, only this area is reflected, right? So having this the reflected pattern on the substrate, we can develop the images. So this is actually the ASML. This is the ASML, the company. This is only the company who provide this the extreme UV scanner. Okay, this is actually the images. Okay, so when you look at this, the extreme UV light source is here, and then go to meters. Okay, and then projection meters, and then eventually where? Here is the wafer. Okay, wafer is the placed in here, coming this the complex the passage, and then eventually these the meters give the light onto here. So this is the extreme UV stepper. So having the resistors, okay, and then having the sample on here, and the mask, and then we can have the nanometer patterns. How much the cost of this the scanner? It's around $120 million. One system, the cost is $120 million. Okay, so you know how much budget of our university? Our university budget is $190 million. In 2020. So whole university, very close to the whole university budget is applied to have this the one system. So now the industry is Intel or Samsung. they spend around 50% of their budget, their money to have this the lithography tool, scanner. Okay, so almost 50% of the cost of the manufacturing of the IC, like Intel Pentium processor or the memory sticks or the computer chips. Okay, 50% of the cost is from this stepper. Okay, so having this one, now what? How much fine pitch can be generated? 16 nanometer level pitches. Okay, so 16 nanometer, this the small size, the pattern can be developed. Okay, so okay, but what? This is the recent announcement, 2020 January 3. You know, Samsung, they announced their first ever 3 nanometer gate around, all around field effect transistor semiconductor. Okay, this one is this. Okay, this is the planar, the FinFET. Okay, it's called the FET, field effect transistor. Gate means the switch. Okay, you learned about the gate, right? Okay, this switch. Okay, the competition in industry is how we can make this the gate small. Okay, okay, so this is another type of the gate. Okay, having this one. Okay, current the Pentium chip used 7 nanometer gate. This the FinFET gate. Okay, now Samsung is now asking the telling us the 3 nanometer the gate. Okay, so the making this the 3 nanometer, now the what they can produce double. Okay, the produce the double the number of the transistor on a same wafer. So that means they can cut the price even down to half. So the actually making small the transistor, yeah, is the best way to win the market. So that's why. So, but how the 16 nanometer level of the lithography can make this the 3 nanometer the field effect transistor. Actually they use very tricky method. Okay, having the 16 nanometer in here, and then it's called the space, and then some of the plasma etching process combined, they can make this the 7 nanometer the gate. Okay, it's their pattern technology. I think this pattern was given by the Samsung, the developed by the Samsung. But anyway, so now the Samsung is put another idea. Now putting this the gate, now the 90-degree rotated. Okay, now these gates are aligned in this, right? So the having this the thin layer, 3 nanometer. Okay, now they can make the transistor, yeah, with these small features. So there are a lot of the very intensive the competition is in the industry. So, but you are now learning the basic idea of the lithography. But yeah, idea is a kind of the lithography, but they are using now a little bit advanced technology. But now you are learning, yeah, fundamental. But now after learning about these fundamentals, now you're going to take over the job in the industry of the semiconductor industry jobs, and then actually you can be the one who will develop the next generation of the transistors. Okay, those are the two. Actually, the immersion lithography is a kind of a little bit outdated. And then this the extreme UV lithography now currently now the front end. Okay, now people are thinking now this the X-ray lithography probably can be the next. Okay, but it's because you know that this one X-ray lithography used 1 nanometer. EUV used 13.5 nanometer. This is the extreme UV. Okay, immersion used 1 to 3.3 nanometer, right? So now this one go. Now people think the X-ray lithography may be the one next, but let's see. This has the many different issues. So still, yeah. For the X-ray lithography, they used a very special mask. And then another one is I told you the E-beam projection is being used. This one case that it can achieve the pattern below the 10 nanometer. How this can happen? I told you EUV can go down to 16 nanometer so far, right? Okay. The E-beam projection can go down to 10 nanometer. How they can do that? They use the electron beam. Okay. There is an electron gun, and then electron is coming out from the electron gun, and using magnetic field, we can control this one on the substrate. Okay. So beam quality can go down to 1 nanometer. Okay, so the few nanometer having the secondary electron, we can go down to 7 nanometer or 1.2 nanometer also. Okay, this is good, right? So compared to this, the EUV 16 nanometer, extreme UV 16 nanometer, still E-beam lithography can go to 1 or 2 nanometer the resolution, right? This case, the what? E-beam lithography doesn't use the optical system. We don't have to worry about the depth of focus. Okay, depth of focus only the matter of the numerical aperture of the lens, but this use the magnetic lens. Okay, so this totally different system. So having this one, okay, yeah, we can have the photoresist in here. Okay, and then having this the beam all about. This is called the raster scan. This case, we can stop, expose, and then turn off the E-beam, and then go and then turn on again in this, turn off, turn on again, turn off, turn on again. So we can develop some of the pattern at this point, okay, by turning on and off while scanning this back and forth, okay? So this is called the raster scan. Vector scan case, it goes directly to the pattern, only right only in this area. There are pros and cons for these two different methods, but these are typical writing methods for the E-beam lithography. So using this E-beam lithography, you can see, okay, this is the 200 nanometer. Okay, you can develop this. Even the three-dimensional pattern can be developed. Small feature key even can be added on here. Okay, and you see here is the 50 nanometer string. This is the width of the 50 nanometer. This type of the design also can be developed easily by the E-beam lithography. You know what's the problem of this? Okay, even though you see 3 nanometer pattern, 10 nanometer can be generated. You know what's the problem of this? Can anyone the type? Okay, what is gonna be the issue in this the E-beam lithography? You know the when you do the coloring, okay, you have a lot of experience of the coloring, right? If the pen, if the pen is thick, you can cover, you can the paint, well, you can color the some of the image quickly, right? But now what we want to use the more finer and finer pen, right? To make the very fine features, right? That means to the color, all the patterns, it takes so long, okay? Okay, so color fringing also, and also it takes so long to write the patterns, okay? So this, the E-beam writing method is good for research, but not for mass production, okay? You know, to color all the wafer like a few tens of thousand wafers, okay? We cannot use this, the E-beam lithography, okay? So there are some of the limitation, okay? And then the another method is it's called nano imprinting. This case, the having having this type of nanometer, the pattern on a stamp, okay? And then this is kind of the nanometer stamp, okay? Having the nanometer pattern on the stamp, and then put the ink, photoresist, and then try to transfer the pattern on the wafer, and then make those type of the things, okay? This is the nano imprinting. So in this case, we can transfer the pattern, okay, multiple times. But the problem is that this actually should contact the substrate, okay? You can cause the mechanical damage, and also you can get the particles on the master itself, okay? It can generate a lot of the problem with those. Even particle can be transferred, okay? Those image can be damaged, and then yeah, the particle can be transferred and repeatedly the generate the problem defect. So that is the issue of the nano imprinting. But concept is wise is pretty good, right? Yeah, you can easily develop these type of the patterns, but like I said, the defect can be the problem. So we went through, yeah, those type of the new technologies. I hope you get some good idea what is going on in the industry, and then what kind of researches are being done in the universities and many the research institutes for this to develop the technology of the lithographies. Now what I'm going to talk about is the how. Now the patterns, yeah, features are getting smaller, okay? We cannot use the microscope to look at the nano scale features. Then we have to use certain tools, right? To measure and then to observe, yeah, the pattern on certain substrate, right? So I'm gonna go over the couple of different type of the characterization technologies. There are three different types. One is the electron microscopes, okay? Second one is scanning probe microscope. Third one is spectroscopy. But mostly I'm going to talk about the electron microscope and then scanning probe microscope, which can measure or the observe the surface structure. This spectroscopy is mainly to analyze the materials, okay? So to see what's going on inside, okay? Like a crystalline structure or some sort of the chemical composition, atomic composition, how they are aligned, okay? What kind of impurities are there, and then how they behave. All those the material, the characterization, the information can be obtained by the spectroscopy, but the methodology doesn't show the lithography pattern or the device patterns. So these two, electron microscope and the scanning probe microscope, we're going to talk about a little bit, okay? So optical microscope, I told you, right? Actually, in the video only showed up to 2000 the magnification, but now the lens optics gets more sophisticated. It can go down to actually see 200 nanometer. It can go down to like 20,000 magnification. Okay, sometimes it's called the super resolution technology is going, then even the little bit go down, the 100 nanometer even features can be observable, but this is kind of the technology can see up to few hundred nanometer the features. Then how can we see sub-nano features? We have to use the electron microscope. Okay, actually I want to show you, yeah, one video. Okay, actually this is the image from center. Okay, actually the center director, Dr. Margaret Monain, is going to give a talk in the conference. Okay, July 21st, she will give a talk. Her center actually got the image. Okay. Okay, I think I should share. Okay, actually this is the individual, you see this, the individual circle. You see these individual small the dots? These are the platinum atoms, okay? Actually, through this the imaging, we can see individual atom, how they are arranged, okay? You see it's a three-dimensional imaging is available now even. So the platinum now this case is the crystalline, okay? So crystallized, so it's periodically it's periodically arranged. It's periodically arranged, okay? So the individual of this, the particle is, the size is how much? Is 2 to 3 nanometer. That means how many the platinum particle arranged in here? It's around 20 to 25 the platinum particle can arrange in here, okay? So total, each particle has how many? 600 atoms. So 600 platinum atoms, yeah, can be arranged in the crystalline in this the platinum particle. But what we can see, actually, you can see how they arranged. Okay, so that is the available by what? By electron microscope. Okay. So this electron microscope, the idea was based on the electron, right? Yeah, electron was discovered by Thomson, right? And then the many theory, yeah, was developed, and then what the first commercial SEM was the around 1960s, right? Okay, so after having this, the old microscope, okay, and then now this is kind of the commercially available the SEM. Actually, this the system is now in our the clean room. Okay, so this our Dr. Kevin Santiago will show you how this system can operate, and then show the image of the nanoscale features, and also the how can measure the photoresist patterns using these tools. Okay, but yeah, and also I'll get back to you. Okay, all right. So this scanning electron microscope much better resolution and depth of field, okay, than the light optical microscopes, okay. And there are some of the issues, okay. So to have the image well, actually this system should be under the vacuum, the high vacuum normally, and then some of the surface should be conductive. Okay, some artifact is generated, and then some visualization problem, two-dimensional the visualization normally. But what? The limitation of the scanning electron microscope are mostly overcome. Okay, many of these the problems are being solved. Okay, so one of them is the one that I showed you in the video, and actually there are many technologies now solving these problems. So scanning electron microscopy is more like the E-beam lithography. Okay. So one question is I got one question. Why is the specimen in a vacuum disadvantage? Because the sum of samples we want to measure in the liquid. Okay. So actually the previous the platinum particle, this was actually flooded in a liquid. Okay, this particle cannot be placed on the surface well. Okay, and then maintain the position well. It's very difficult. And then actually this particle was floated in the liquid. And also, you know, some of the DNA biomolecules, you know, so that should be sustained in the liquid, right? Biological medium, right? So to look at those type of things, the liquid cannot stay in the vacuum well. Okay, so that is kind of the disadvantage. But now, what? Like I said, many problems are being solved now. Yeah, some of techniques are developed. Now the some of samples in the scanning electron microscope, the some of samples in the liquid can be observed well by this SEM, scanning electron microscope. So like I said, that the electron gun is used. Here is the electron gun. Some of the magnets are here, and then to generate the focus and also to control the beam. Okay, so, and then what? There is a detector. This case is not right only. Okay, there is a detector, so we can see the substrate features. Okay, this is the electron gun. Okay, this by making this sharp tip, okay, we can get the electrons from this tip by applying the electric field or by applying heat. Yeah, so to generate the electron, okay, from the tip of the electron gun, the two different methodology can be applied. One is the thermionic emission or the field emission. Thermionic emission means heating. By heating the substrate, you know, then the electron can have enough energy to overcome this work function. Okay, so then get into the vacuum level. Okay, this work function can be overcome by what? By heat, or by having very high electric field in between the tip and then the electrodes. Okay, we can take out the electron. Okay, so the high electric field is used to get the electron. Actually, the field emission is much better to control the energy. Okay, so you can see now the resolution using the conventional SEM using the thermionic emission, but the field emission you see much better clear image can be obtained, and the resolution is much better. You see the force, the comparison of these two, right? So like I said, that this electron, once this electrons comes out from the gun, okay, then we need to control these electrons, right? So making them into a focus, okay, or we need to scan this beam to see the images, right? How we can control this electron? I think you learned about the Lorentz force, right? Yeah, but when the electron travels certain direction, if we apply the magnetic field, then these electrons face certain force. That is the Lorentz force. These charged particle, subject to certain force, right? By applying the magnetic field, right? So we can control the G direction. We can control the theta direction in the cylindrical coordinate, and then also we can control the R directions force by applying the magnet, and then by combining this magnetic by arranging this magnet and then controlling the magnetic current and then magnetic field intensity well, then actually we can focus the beam and then we can scan those type of things well. So this is called the electromagnetic lens. So did again having this cathode, okay, electron beam coming out through the condensing lens, we can make the second condensing lens, we can focus well, and then using the electromagnetic coil, yeah, we can just control the beam on here, and then having these the sensors. Okay, this is the detector. Okay, so we can see, and also we can analyze what's inside. Okay, so when the electrons comes into the certain surface, because the electron has very high energy, okay, it react with the top surface, okay, and also penetrates through this material, and then scatters scattered by the inner core, the electrons and also atoms. Okay, so many scattering happens. Okay, by this is the incoming electron by interacting with the atoms inside. Okay, and then the atom has many electrons, right? So when the hit the internal the surface atoms or internal atoms, it react with this electron and generate take out the electron from the atom and generate the secondary electron. Well, some case it goes deep inside and then coming back. It's called the backscattering. Okay, this electron comes back and then the backscattered electron goes back. Okay, and then actually the backscattering gets some of the internal structure information because depending on the atoms, this backscattering energy changes. Okay, so okay, this electron can have many different energy level, very shallow, small energy, also very big, the large energy. Okay, so the small energy, shallow energy can show the surface the information, and the backscattered electron with the very high energy can show the information from deep inside. Okay, by combining these two, okay, by arranging these detectors, this is secondary electron for the surface image. Okay, and then having another backscattered electron, the detector on here, we can look at the surface information. Also we can see the structured information from inside. So this is the basic idea about the scanning electron microscopy. There is another one. Even we can see the more details of the structure. So that is the transmission electron microscope. This is the internal, the atomic structure. You see, yeah, the one that I showed you, the platinum, that atom. Okay, arrangement of the platinum atom that I showed in the video, that actually used this the transmission electron microscope. Okay, so I want to give you the information. Actually, the center, actually who has the most advanced TEM. Okay, that is located at the university in Colorado. Okay, the director of this the TEM center is going to give us the talk, a lecture on Tuesday, next week Tuesday. Okay, so don't miss the lecture. Okay, he's going to explain how the transmission electron microscope is going to operate. He's going to explain you the state of the art of the transmission electron microscope technologies. Okay, now I want to show you one video. Okay, what I'm going to show you is, okay, what I'm going to show you is using the scanning electron microscope, how the thickness or the width can be measured. Switch. Okay, this is actually the system is used in the industry. Okay, this robot is taking out the wafer. Okay, this is the 12-inch wafer. Okay, from a cassette. Okay, and then put into the system in the scanning electron microscope. Okay, to put into the scanning electron microscope, this robot has to align the wafer very well. So it takes time now. Now the door was open here, right? Door was open. This is the SEM chamber door. Okay, put into the SEM, and then now evacuating the chamber now. Okay, after closing this door. This SEM is operated under the vacuum. Okay, now now the wafer is placed under the electron gun. Now you see these the features, right? It's being loaded. Yeah. Okay. Okay. It's vacuum taking time. Okay, I will go over this the parameter a little bit. Okay. Okay, now in the industry, this is the 12-inch wafer. Okay, 12-inch diameter wafer. Now these are the fields. Includes the chips. Like Pentiums are chips are made in this the box. Okay, individual box are arranged by lithography technology. Normally in the industry, they measure normally this the 5 points, center and then all around. Okay, top and bottom and the left and right. Okay, and then they measure these the patterns on this yellow, and then also certain the fields. This is the field, name is field, measured. Okay, for certain purpose. Okay, now the wafer, you see wafer, current wafer, the beam is now in this way on this wafer. Now current, this SEM is now looking at this pattern. You see this is the current. Okay, this yellow are inspect. Okay. 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 To observe this, the pattern, it used optical microscope first. Normally, this system incorporate two different microscope. One is the optical microscope, OM. The other one is SEM, scanning electron microscope. Now is the optical mode because to find out the pattern, we need to look at more the broad way, right? We don't want to the look around the very small area to find the sum of the pattern, right? Look at overall features under the optical microscope and then go into the very specific pattern and then do the measurement, right? So first, optical microscope is used to find certain pattern, right? Okay, now they found optical microscope. Now it's the magnification is now 100 times magnification. Now they switched into SEM. Okay, now by having SEM, now the magnification is 5,000. Okay, 10,000 now. They changed the 10,000. Okay, to see the details of this pattern. Now under the 10,000, they can easily see this the pattern. Now the 8,000 magnification to see some of now 20,000 magnification. They want to measure the width. Actually this the spacing. Okay, the measures. Now, okay. Okay, just okay. I want to go back. I clicked the wrong button and then okay. Okay, using the SEM, we can measure okay the height and actually the width. Okay, by scanning the beam along this and then looking at the reflection of the electron beam. Okay, we can see. Okay, so this is around 2 micro pattern. Okay, so this type of the measurement can be done by SEM easily. Okay. and then go to another pattern to figure, and then we want to see details of this, and then changing into the SEM, scanning electron microscope, you can see these type of the patterns, right? So, and then what? We can go down to further, okay, the final features in different point. Now the magnification is how much? 190K, okay? Okay, it's like a 200K, 190K. This type of the magnification can be easily made, okay? All right, so these type of the tools are being used in industry, and also we have this tool for the research and then for training purpose. Okay, so these are the kind of the way of the looking at the nano features. Okay, so just a minute. I want to go over one more technology and then I can wrap up this class. Okay. This one is the electron microscope. And then another way is it's called atomic microscope and surface profiler. Okay. What is that? Is the having this the very sharp tip. Okay. Okay, with the sum of spring. Okay, we can scan this the sharp tip on the surface. Okay, and then depending on the surface structure. Okay, we will see many different type of the light reflection. Okay, by looking at that. Okay, we can see whether this is the tip, whether this tip, when this tip go over this the particle, actually we can detect the tip motion, right? And then by doing so, we can check we can push this one, we can push to the side, or we can pull this one to the top. So we can do many things using this the very sharp tip, right? So this is called atomic force microscope. Okay, having this one, okay, by scanning these the two circles, okay, with this sharp tip. But if we make the sharper tip, we can see better, right? We can see resolve this the distance, right? So making sharp tip is important. Okay, sometimes we have to use the very thick tip, okay, to see the rough surface. But sometimes very sharp tip is the good. Okay, particularly is the ultra level is being used to measure the 10 nanometer the type of the tip. Actually, even the tip side go to couple of nanometers. Okay, so having this the scanning and then touching the surface, we can have this type of the force distance curve. Usually it's not, we don't want to go through. This is the one normally the AFM is using to measure the surface, okay? We can have this, the sharp tip on the surface, and then actually the scan through the surface structure. Having this, the scan structure, we can get the information of surface like this, right? This is the direct contact modes, okay? We can make this tip contact directly on the surface. The other one is like I showed you, using this the force distance curve. Okay, even the small van der Waals force. Okay, atomic force between this tip and the surface can be measured without contact. Without contact, having this the small gap. Okay, we can have the surface information. This is the non-contact method. Okay, the other one is the vibrating. It's tapping. Having the tip on this surface by tapping very often, okay, then we can have this information surface, okay. So each one has the pros and cons, okay. This can be used for the very, the steep surface, and also some of the large surface area, okay, not much the affected by the surface material, but the some of the limitation for the sticky material, okay. But this case has some of the good information of the the small features, and also damage is small. Okay, but the control of this one is very difficult. So there are, each one has the pros and cons, giving the different information, but the atomic force microscope can give you the nanoscale surface. And also the profilometer, okay. This is the atomic scale, but for the practical use in the industry to measure some of the step height, not like the nanoscale features, sub-nanometers, sub-micron, these are large size features, the profilometer can be used. This case, having this scanning with large features compared to the previous atomic force microscope tip, this feature has very large tip, okay? So, but still, the 300 nanometer, those type of the things can be measured, okay? Actually, we put this video in the Blackboard, not in the Blackboard, Google Drive, and then we put a link. Please watch videos for this profilometer. Then you will understand how the profilometer can be useful, okay? Can be used in the industry and for research. I think these are all, okay? You watch this video, okay? So now I want to have some of the questions from you, okay, about this class. Okay, do you have any question? Okay, one question, what's the benefit of decreasing the resolution in immersion lithography? Because we can make, smaller transistors. You know, 12-inch wafer, if we can make the 100 chips at a time, by making the smaller features, half size of transistor, you can make actually the 400 chips at a time. So the cost can be dropped down to 25% like that, right? So that's the benefit of the making smaller features using immersion lithography. Okay, so how does the sharp tip not damage the small features? You know, the small features, actually the surface itself also hard. Some case they have to scan the very hard surface. So the atomic force doesn't make much damage on there. Even though there is some of the damage, only very small point, test point. So it doesn't give the impact to the production devices, okay? So many different ways, but the tapping mode case, it's pinpoint. Okay, only that the point can get the mechanical impact. Okay, you can reduce the damage instead of the scratching, right? Surface the scanning, right? And also the non-contact method, it's gonna be the actually the minimal, okay, impact to the surface structure, right? So yeah, if you don't want to give any damage, then you choose the non-contact method, okay? That doesn't generate any the damage, or the very minimal damage in the substrate. If you don't consider much of the damage on the structure, because only you measure very small area, okay, representing the characteristic of the surface structure. If you don't care the damage, then you can use the contact method or tapping method. So it's depending on the choice.